Hey guys, we're back today to talk about the areas and volumes of similar solids. I added something new in that I gave you the standard that Miss P had on this assignment in your first slide, just so you can connect that back to where you are in Empower. When we're looking, the first thing that we need to talk about today are actually what similar solids are. And it's a really simple definition, the same that you've used earlier in the year. Similar solids have the same shape, and all of their corresponding dimensions are proportional. For example, it could be the radius of the circle on the ends of the cylinder needs to be proportional with the height of the circle. Again, their circumference would be proportional. All of the parts of those need to be proportional. So in a cube, we're always talking about length, width, and height. Those would need to be proportional for our cube to be proportional. So when you're looking at these, it's very simple and straightforward. To determine if the two are similar, you compare their corresponding sides, just like you have done before when you were looking at similar triangles or similar figures earlier in the unit, or excuse me, earlier in the year. You're going to look again at these guys to see if they're proportional, but instead of looking at just 2 dimensions, you're going to be looking at 3. So it's really simple, straightforward. The length of the first figure over the length of the second figure. You can see here, like this would be a length of 3 compared to a length of 6. Then it would be the width of the first compared to the width of the second. So this would be 2 to 4. And then the height of the first compared to the height of the second. You can see on each of these corresponding sides, we get the same ratio. So 3 divided by 6 is 1/2. 2 divided by 4 is 1/2, and 3 divided by 6 again is 1/2. Since all 3 of those sides produce the same ratio, that tells us that they are, first off, similar, and second off, it tells us that their scale factor is 1/2. Now the theorem that goes along with this is really quick and simple, and it says that if the scale factor of 2 similar solids is A to B, so one side to the other, like in our previous example it was 1 to 2, then the ratio of their corresponding areas is A squared to B squared. So in our last example we had A to B was 1 to 2, so in this example we would have that 1 squared to 2 squared, which would give us a 1 to 4 for their corresponding areas. And then again we'll see a similar setup. The ratio of their corresponding volumes is then A cubed to B cubed. So it shouldn't surprise you at all that if it's a solid flat shape, it's an A to B ratio. When we talk about area, it's squared. When we talk about volume, it's cubed. So next we're going to work out a couple problems, but before we start then, I brought you guys a cute little math joke again. Okay, let's try a couple problems on these, and then you guys will be set to work on your homework. Okay guys, so we're back over with a practice problem here. You can see that I have drawn 2 similar, or potentially similar, I should say, solids. These are cylinders. And you can see that we've labeled the radius on one is 6, the radius on the other is 5, the height on one is 12, and the height on the other is 10. So when we're looking at these, our 3 questions so far are the 2 solids similar? If so, find the scale factor. And then what's then the ratio of the areas and the ratio of the volumes? So when we're looking at this, I did also leave myself a little sticky note here as a reminder of my ratios. So as I'm going through, I'm going to look at the ratios of the corresponding parts. So in cylinders, we compare radii and height. So on the first one, I have a radius of 6 and a radius of 5 on the other. When I reduce that, I cannot reduce that any further. 6/5 is as far down as we can go. And so that's my comparison for the radius. And then the other one, I'm going to again look, my height has a ratio of 12 to 10. So when I look at height, comparing 12 to 10, which I can reduce, can divide both by 2, and that gives me a scale factor of 6 to 5. So my scale factor is 6 to 5 for both parts. Therefore, these are similar figures, and the scale factor is a scale factor of 6 to 5. Now, when we're looking for the ratio next of the areas, we can go back to our theorem from earlier and know that if they have a ratio of 1 or A to B, then the ratio of their areas will be a squared to b squared, and the ratio of their volumes will be a cubed to b cubed. So on this place, my a is 6, my b is 5, so I'm going to go ahead on my second ratio for the area. It's going to give me 6 squared to 5 squared. It should give me a 36 over 25 for my areas. If I think about those, I need to reduce that down at all. I can't think of a number that would go into both 36 and 25, but we'll keep thinking about it. And then when I'm looking at the volume, I do the same, except I'm going to go ahead now and have 6 cubed and 5 cubed. So if you don't remember what your cubes for those two are, you can, as always, grab your handy dandy calculator. And on these 6, the easiest way to get a cube is to use your caret symbol, which is right down here. So you can go ahead and use 6. I'll put it over there so you can see it a little better. So we can use 6 with a caret of 3, which will give us 6 raised to the power of 3, which turns around and gives us 216. And then we can do the same 5 raised to the power of 3, and that gives us 125. So then I'd need to do any reducing if possible, but I don't think there's going to be any. So I'm going to go ahead and call this the ratio of my volumes and the ratio of my areas. And that's it for that problem. This one we have one more setup with our volumes. So we have two solids, and we're given the fact that they are similar. We're given the volume of each of those solids, and we're asked to find the ratio of their volumes. So when we're looking for the ratio of volumes, we know that it's the cube of both of the volumes. So we can go ahead and fill that in with the smaller, just 729, over the larger, just 1331. And then we need to take the cube root of both sides in order to solve for A and B by themselves. So I can go ahead and cube root these separately. Remember your brother and sister rule, whatever you do to one side, you have to do to the other. So when we go through here, I'm going to take A cubed and take the cube root of it. Sorry, I forgot my cube. When I take A cubed and then take the cube root of it, I'm left with just A. And I do the same with B cubed, left with just A over B. Then I can use my calculator to find the others. So to get a cube root, some students know already, but you go down to the fourth option under the math function, and you'll see that it says the cube root right there. So when I put that in, then I simply add my parentheses, and it tells me the cube root of 729 is 9. I'm going to do the same, so the math key, and then you can either arrow down or press the number 4 to get the cube root again for 1331. That gives me 11. So the ratio of my two figures is a ratio of 9 to 11.